Okay, thanks for coming to my channel. My name is Linus Antonio Forejekum. This is going to be the first part of a 6-lecture series on Electronics 2 for HND. So this is going to be the first lecture, which is lecture number 1. And here we're going to look at amplifier classifications. Before I begin, to make this lecture more engaging, please feel free to subscribe to my channel, Linutech. And then also, anytime we post videos, you would be able to see them. And again, as you go through this lecture, wherever you have questions or wherever you have doubts, if you don't understand anything, feel free to leave me a question under the comment section, and then I'll take time to respond and clarify wherever your doubts are. So in order not to spend so much time, let's dive into what is ahead of us in terms of amplifier classifications. Yes, so amplifier classifications. Before we go into amplifier classifications, what we'd be asking ourselves is that what are amplifiers? What are amplifiers? Or what is an amplifier? Basically, an amplifier is an electronic device that accepts some form of input signal and then gives us a bigger version of that input signal. So for instance, if this block here is set to be an amplifier, and we have an input and we have an output here, assuming the input here is A, if it goes through this amplifier, this amplifier would have something we call the amplification factor or gain. That is the amplification factor or gain. Okay, now this gain or this amplification factor will be multiplied by this input so that we would have a bigger version of this input at the output. Okay, so it is just basically, let's take for instance, in this amplifier we have an amplification factor of, let's say, 2, and the input here is, let's say, 10. What would then happen is that our output is going to be 2 times 10, which will give us what? 20. So at the end of the day, our output is what? 20. Alright, so that is basically what an amplifier does. Now let's move on to the main topic of the day, which is amplifier classifications. Yes, there are different ways we can describe amplifiers. If you have looked at amplifiers that were built from BJTs or FETs, you realize that these amplifiers come with different common terminal configurations. So yes, amplifiers can be classified in different ways, or they can be described in different ways. They can be described either by their interstage coupling, that is to say, from one stage of amplification to the other, what is used to couple stage 1 of amplification to the next stage, by the type of amplifier element used, by the type of signal they are designed to amplify, and also by their frequency range. So we're going to look at some basic classifications of amplifiers, and then we're going to look at them in terms of common terminal. We would also look at them in terms of the operation they perform, and then we'll also look at them in terms of their output properties. then the signal in terms of their frequency response, and then their interstage coupling, their mode of operation, and then the type of signal, be it a small signal or a large signal. So we're going to look at them in that regard. So in order to move further and not spend much time here, let's quickly look at the first item on the block, which is the classification of amplifiers in terms of their common terminals. Now, one set of classification for amplifiers is based on which device terminal is common to both the input and the output circuit. If you would remember, in electronics 1, we looked at BJTs, which is bipolar junction transistors, where we looked at the NPN and then the PNP transistor. Okay, now you would remember that we had three terminals, or we have three terminals for the BJT, that is the collector, the emitter, and then the base. Okay, so amplifiers that are built out of BJTs could be classified based on their common terminal, whether the base is common, whether the collector is common, or the emitter is common. If you would recall, when we're looking at BJTs, we looked at BJT configurations, where we looked at the common base configuration, we looked at the common emitter configuration, and then we looked at the common collector configuration. Okay, so we can actually classify amplifiers based on what the terminal that is common to the input and then the output. Same way for FETs or FETs, or field effect transistors. In full, you would remember that we have the drain, we have the source, and then we have the gate. Okay, so similarly for BJTs, the FETs could be classified based on their common terminals in terms of their input and output circuits. Okay, so that is one way of classifying amplifiers, based on their common terminals. The other one we would look at, or we want to look at, is a type of operation performed by the amplifier. And a typical example is the op-amp, which simply stands for operational amplifier. Okay, now operational amplifiers are used for so many applications. The basic ones you can think of is using them as summing amplifiers, integrators, differentiators, etc. Now here, for operational amplifiers or op-amp, they are used to perform mathematical operations. They are used in instruments and for signal processing as well. Okay, so for op-amps, they are used, or they can be used for what? Mathematical operations. So that is an example of operation the amplifier performs. Then the second one would be that they are used in signal processing. Signal processing. Okay, now example of configurations you can have for operational amplifiers is for them to be put together to perform as an inverting amplifier. That is to say, if you say you give it a positive input, it will give you an output which is negative. In most cases, we look at that when you look at digital circuits as NOT gates. They can also be used for summing amplifiers, where you have two input signals and you want to sum them up. Op-amps can also be used. So in terms of the operation amplifiers perform, you can also use that to classify them. Then another thing we would look at is classification based on the output properties of amplifiers. As we recall in our previous lectures in Electronics 1, you would remember we calculated gain in terms of current, power, and then voltage, which meant that amplifiers would have output properties in terms of voltage, in terms of current, and then power. Okay, so whatever the tax, there are three main categories of amplifiers that relate to the properties of their output, and these are basically voltage amplifiers, current amplifiers, and then power amplifiers. Okay, now amplifiers are used to increase the amplitude of a voltage or current, or to increase the amount of power available, usually from an AC signal. Okay, so with input and output in the same units, if you recall, we calculated the gain of an amplifier, AV, for instance, if this is voltage gain, to be the output voltage divided by the input voltage. That would have been the gain for a voltage amplifier. Okay, so with input and output in the same units, gain we normally would say is unitless. But in some cases, however, the input and output signals of interest are not of the same units. So for instance, for a transconductance amplifier, okay, the input controls the output, okay, current, and the gain is expressed as, so in this case you have the gain to be equal to the current output divided by the voltage input. Okay, that is for a transconductance amplifier. So you would realize that in some cases the gain of an amplifier cannot be said to be unitless, but the basic principle of gain is that gain is unitless. But in this case, for a transconductance amplifier, we would say that it is not unitless. Okay, all right, that is that the gain has unit of what? Conductance, output current per unit voltage. Similarly, for a transresistance amplifier, okay, where you have transistors and resistors dominating the circuit design, the amplifier has a unit of what? Resistance. Okay, so with regards to output properties of amplifiers being the basis for their classification, it could be current being the output, voltage being the output, or power being the output, based on whichever we can classify them based on the output they produce. Okay, all right. Now, when it comes to types of signals, amplifiers can also be classified depending on the type of signals. Okay, one way to describe an amplifier is by the type of signal it is designed to amplify. This usually refers to the band of frequencies that the amplifiers will handle. In some cases, the function that they perform within an electronic circuit. So an amplifier could handle signals like audio frequency, and such amplifiers will be termed as what? Audio frequency amplifiers. We could also have intermediate frequency amplifiers handling intermediate frequencies, radio frequency amplifiers being used to amplify radio frequencies. We also have ultrasonic amplifiers, wideband amplifiers, video amplifiers, DC amplifiers, and then tuned amplifiers. We're going to look at these one by one and then see what they have for us. Okay, so let's take them one by one in this case, and then we'll look at audio frequency amplifiers, audio frequency amplifiers, alright. So for audio frequency amplifiers, these are used to amplify signals in the range of the human hearing, okay? And then the frequencies within the range of the human hearing is 0 kilohertz, it's approximately 20 kilohertz. 20 hertz to 20 kilohertz. Okay, that is the audio frequency range. Okay, so for audio frequency amplifiers, these amplifiers can amplify signals within the range of the human hearing, which is the range of human hearing, within the range of human hearing, and the range of human hearing is 20 to 20 kilohertz. Okay, all right. Now, in some cases, although the audio frequency amplifiers would amplify signals within these ranges of 20 to 20 kilohertz, there are some hi-fi audio amplifiers. When we say hi-fi, all that it means is that high fidelity audio amplifiers. Okay, and these amplifiers extend the range to about 100 kilohertz. Okay, whilst other amplifiers may restrict the high frequency limit to about 15 kilohertz or less, which is within the 20 to 20 kilohertz frequency. But for high fidelity, which is usually used to produce very high audio frequency outputs or amplification, they would normally do amplification to up about 100 kilohertz of frequency. So that is it with audio frequency amplifiers. So now we would move on quickly to intermediate frequency amplifiers. Intermediate frequency amplifiers. Intermediate frequency amplifiers. Okay, or in some cases they will say the IF amplifier. Now, for the intermediate frequency amplifier, it operates at a frequency lower than that of the radio frequency signals. Okay, now, but it's also higher than that of the audio or video signals. The frequency at which intermediate frequency amplifiers operate and the bandwidth of the amplifier depends on the type of equipment. So, for example, an AM radio, which is an AM radio receiver, the intermediate frequency or the IF amplifier the IF amplifier operates at around 470 kilohertz, and their bandwidth is normally, that is the frequency, have to be around 470 kilohertz with a bandwidth of usually 10 kilohertz. That is to say that if you take the frequency spectrum, it could be between you're looking at 400 and let's say 65 kilohertz to about 475 kilohertz, where you already know how to calculate bandwidth, where you take BW will be equals to F1 minus F2 minus F1, which is equals to, in this case, just a second, in this case 475 minus 465, which would leave us with a frequency of 10 kilohertz to be the bandwidth. Okay, while for TV commonly uses 6 megahertz. So for radio we have 460 kilohertz or 470 kilohertz as our frequency, around that figure. And then for televisions, we would have a frequency of about 6 megahertz. Okay, 6 megahertz. And then the bandwidth is usually around 30 to 40 megahertz with a BW of 30 to about 40 megahertz. Okay, all right. And in radar, it would normally have a bandwidth of 10 megahertz for radar applications. Okay, so usually for intermediate frequency amplifiers, that is their characteristics. And then also we have, with respect to ultrasonic amplifiers, so with ultrasonic amplifiers, so for ultrasonic, which is ultrasonic amplifiers. Ultrasonic amplifiers are the type of audio amplifiers handling frequencies from around about 20 kilohertz to about 100 kilohertz. So from 20 kilohertz to about 100 kilohertz, we would look at it to be an ultrasonic amplifier. And they are usually designed for specific purposes, such as ultrasonic cleaning, okay. And then 2, they are also used for metal fatigue detection. So for metal fatigue detection, when we say metal fatigue detection, what we're trying to talk about is basically when the metal is stressed or when the metal gets weak. And then they are also used for ultrascan. Remote control systems also use ultrasonic amplifiers. So the fourth application would be remote. Sorry, my screen touch is too sensitive. Okay, so we have that as well. Now, that is it for ultrasonic amplifiers. We can move on then to look at wideband amplifiers, which is also a means or the type of signal amplifiers can amplify, based on which we can classify them. So in this regard, let's look at wideband amplifiers and then see what features they also have. So for wideband amplifiers normally have very precise amplification factor over a wide range of frequencies. Okay, so normally what happens is that they are used to boost signals for relay in communication systems. Okay, so for wideband amplifiers, for wideband amplifiers, just a second. So we're going to look at wideband amplifiers. So for wideband amplifiers, they're usually used for precise amplification, and normally they are used in communication, systems. Okay. A narrowband amplifier is made to amplify only a specific narrow range of frequencies to the exclusion of other frequencies. So for a wideband amplifier, it must have a constant gain from DC to several tens of hundreds of megahertz. They are used in measuring equipment such as oscilloscopes. So they are also used in measuring equipment. They are also used in measuring equipment such as oscilloscope, where there is a need to accurately measure signals over a very wide range of frequencies. Okay, so that is why we name them wideband amplifiers. Alright, then we also have video amplifiers. Basically, for video amplifiers, there are special type of wideband amplifiers that are also preserved, or they preserve the DC level of a signal and are used specifically for signals that are to be applied to cathode ray tubes or CRTs, okay, or other video equipment. The video signal carries all the picture information in the TV, video, and radar systems. The bandwidth of video amplifiers depend on the kind of frequency or the amplifier used. In TV receivers, the frequency normally, or the bandwidth, extends from about 0 to 6 megahertz, and it's wider still in radar, or in radar communication you can have the frequencies going far up. And then we also have DC amplifiers. Now, DC amplifiers are used to amplify DC voltages, that is 0 hertz. Direct current signals would normally have no frequency, okay, or very low frequency. So DC amplifiers are used for such amplification, and it is very important. They are very common in electrical control systems and measuring instruments. So these are some of the examples of amplifiers that can be classified based on the type of signal. So we have the audio frequency amplifier, the intermediate frequency amplifier, the radio frequency amplifier, ultrasonic amplifiers, wideband video amplifiers, DC, and then we have the tune amplifier. So let's look at the tune amplifier into detail. Now, tuned amplifiers are amplifiers involving a resonance circuit and are intended for selective amplification within a narrow band of frequencies. Okay, for example, for radio and TV amplifiers, so tuned amplifiers are employed in radios and televisions. Okay, all right, so radio and TV amplifiers employ tuned amplifiers to select one broadcast channel from among the many concurrently induced in an antenna or transmitted through a cable. Okay, so like it said earlier on, tuned amplifiers are amplifiers involving a resonance circuit and are intended for selective amplification within a narrow band of frequencies. Examples of where you can find tuned amplifiers are in radios and in televisions. So these are some applications where you can find tuned amplifiers. Now let's consider the ideal parallel RLC circuit above. This circuit is considered to be an ideal parallel circuit. So we're going to do some analysis with this parallel circuit to derive some equations for the tuned amplifier, which we would use later on in our calculations. So for the circuits in here, let me redraw it here for the purposes of our analysis. So this is a capacitor, this is an inductor, and this is a resistor. So we have an impedance here. Okay, so for this we can say that the impedance, which is Z omega, is equals to 1 over R into bracket J omega C minus 1 over J omega L. That would be the impedance that the circuit produces. Okay, now at resonance, that is when the impedance is minimum, we can say that omega C is equals to 1 over omega L. And then the resonance frequency, which is omega R, is given by omega R squared is equals to 1 over LC. Now, if that is the case, to find omega R, we would then take the square roots of both ends. So if we take the square root of this side and we take the square root of this side, this will cancel this, we'll be left with omega R. Square root of 1 still remains 1, and then square root of what? LC. So that is how we get our resonance frequency. So our omega R, which is resonance frequency, omega R would then become 1 over square root of LC, which is usually measured in radians per second. Okay, now if we are to look at the frequency in hertz and relate it to the angular frequency, then we would say that omega, which is omega is equals to 2 pi f. Okay, we would then say our frequency in terms of hertz and relating it to the angular frequency would give us 2 pi f. So if that is the case, we know already that omega squared omega R squared is equals to 1 over LC. So if that is the case, then we can say that 2 pi f in this case, because we're looking at resonance frequency, let's make our F to be FR. Okay, so the whole of this squared will be equals to 1 over LC. Okay, so in that case, we're going to have 4 pi squared FR squared equals to 1 over LC. So to make our resonance frequency in terms of hertz, the subject would have 1 over 4 pi squared LC. Taking the square root of both sides, again this will cancel this. This will still remain 1, so we'll have FR equals to 1 divided by the square root of 2 is, sorry, the square root of 4 is 2. And then, of course, the square root of pi squared. This will cancel, so we'll have pi, and then we'll have root LC. So that leaves us with the resonance frequency for a tuned amplifier. Now, we would look at some other basic terminologies. So now, the resonance frequency, which is the FR, which in some cases is also called as the cutoff or the center frequency. The center frequency. Okay, so in some literature you would see resonance frequency or center frequency. It is the frequency at which the impedance is lowest and therefore the gain is highest. So definitely when at this point at resonance frequency, what we would have is that Z omega is seen to be very small, and thereby giving us the chance to have what? A very high gain, so that we can have a good amplification. So a tuned amplifier is designed to amplify only signals with frequencies that are close to the resonance frequency. So amplification is only for tuned amplifiers is designed, or in order to do amplification, or for a tuned amplifier to have a good amplification, what it means is that the tuned amplifier should have its design to amplify only signals that are close to the resonance frequency FR. Okay, all right. Now, the quality of the tuned amplifier, or in most cases we term it as the Q factor or the quality factor. Okay, so the quality factor, which is the same as Q factor of a tuned amplifier, is equal to the ratio of the resonance frequency against what? Bandwidth, or to bandwidth. So quality factor in this case is giving us ratio of the resonance frequency to bandwidth, which is BW. So BW. Okay, now Q is determined by the circuit component values for a parallel resonance circuit. Okay, and then in most cases we already know that if we are going to determine the Q based on the component values, then in this case we are going to be looking at the resistance, and then the inductance of the circuit. Okay, so in that case, we already know that our FR equals to one over 2 pi square root of LC. But in this case, if we're looking at the circuit components to use that to determine our Q, then we can say that Q is equals to XL divided by R, where R is the resistance and then XL is the reactance of the inductor. Okay, so from here you can see that it is very clear from the above that the narrower the bandwidth, the higher the quality factor from this equation. Okay, from this equation, what we can say is that if the bandwidth is narrow, it means our Q factor would be better. Okay, now the significance of the quality factor is very obvious from this diagram here. Okay, where you have BW1 being greater than BW2, and then you have BW3 being greater than BW2 and being greater than BW1. But you would realize that with the bigger bandwidth, the Q factor tends to be what? Smaller. And then as the bandwidth becomes narrow, the Q factor tends to be what? Bigger, which gives us what? A bigger Q factor, which is actually good for the tuned amplifier. So the smaller the bandwidth, the better the circuit is able to reject frequencies outside the center frequency. The quality factor in this case is therefore a measure of the selectivity of the amplifier. If you remember, we said that the tuned amplifier or amplifiers, tuned amplifiers are amplifiers involving a resonance circuit and are intended for what? Selective amplification within a narrow band of frequencies. Okay, so that is tuned amplifier for you. So in this case, pay particular attention to these formulas. You might need them as we progress. You might need them for some calculations as we move on. All right. So here you realize that the bandwidth here is very big, and that when you trace the bandwidth, you realize that our Q factor in this case is 50. Now, as the bandwidth becomes narrower, you realize that the Q factor increases. As it continues to be very narrow, our Q factor then becomes what? 250. So the smaller the bandwidth, the better the Q factor. All right. Another way of classifying amplifiers is through interstage coupling. Okay, through interstage coupling. Now, interstage coupling of amplifiers are determined basically by the type of material that is used to couple the various stages of amplifiers. And in this case, we're restricting ourselves to 3 types of interstage coupling, which is the capacitive coupling, the transformer coupled amplifier, and then the direct coupled amplifiers. So for the capacitive coupled amplifier, you realize that after the first stage of amplification, moving to the next stage, you have a capacitor which sits in between the first stage and then the next stage of amplification. And this type of amplifier is what we term as what? Capacitive coupling. Okay, this is what we term as a capacitive coupled amplifier. Now, the other one, which is this one, is what we term as a transformer coupled amplifier. Here, the material that is used for the interstage coupling is what? A transformer. That is why we call it a transformer coupled amplifier. Then the third one, which is the direct coupled or the DC amplifier, you would notice that after the first stage of amplification, that it is connected directly to the second stage of amplification, and that is what we term as the direct coupled amplifier. So this is the direct coupled amplifier, and then we have the transformer coupled, and then we have the capacitive coupled amplifier. Then based on the mode of operation, okay, transformers can also be classified based on their mode of operation. Now the mode of operation could either be whether they are a class A or a class B or a class C or a class AB or a class D amplifier. So based on their circuit configuration and principles of operation, amplifiers are classified into three different or several classes. The relationship between the bias voltage and the cutoff voltage of an amplifier is what classifies an amplifier as being either a class A, a class B, a class AB, a class C, or a class D amplifier. Okay, these classifications, or this classification, is one of the most important for power amplifiers, since it reflects the trade-off between efficiency and linearity. So as we move on, we would look at class A, class B, class C, and then class D, and then class AB amplifiers, and then we would look at the efficiency and linearity of these amplifiers and how a trade-off between them actually assists to give us a better output. This will be looked at in chapter 2. Another way of classifying amplifiers would be through their signal size. Okay, and then in this case, amplifiers could be classified in terms of what? Small signal amplifiers, or they could also be classified as large signal amplifiers. Okay, now small signal amplifiers are designed basically to amplify very small signal voltage levels of only a few microvoltages from sensors or transducers or audio signals. However, large signal amplifiers are designed to amplify large input voltage signals or switch heavy load currents, as you would find in driving loudspeakers, the speakers we use at functions. Okay, for an ideal amplifier, or for an ideal linear amplifier, the transfer curve, as you see, between the input and then the output voltage would be a very straight line, which is this red line you see here. That is if we're looking at a linear amplifier. Okay, an ideal linear amplifier, that would be a straight line. And in that case, we can say that the output voltage V0 is equals to the gain times the input voltage Vi. Okay, that is, the output level is simply proportional to the input and the amplifier's voltage gain. Okay, that is, we can say that AV is equals to A1. For a real amplifier, the transfer curve will not be a perfectly straight line, and the relationship between input and output voltage would be represented by a polynomial. Okay, it will be represented by a polynomial of function to represent the output voltage. So for the linear amplifier, we can say that the output voltage is given as V0 equals to the amplifier gain times VI. That is to say, if we have several amplifiers. Okay, now for a nonlinear amplifier, which transfer curve would look like this, the black curve you see here, the transfer function or the output voltage would become a polynomial, would look like a polynomial as what we have here, where you would have V0 equals to A1, which is gain 1, times VI, gain 2, times VI squared, like that, because it is what? An exponential. Okay, it is not linear. All right, where the individual coefficients A1, A2, A3 are the constants for a specific amplifier. Okay, all right. So amplifiers are inherently nonlinear. So very often amplifiers would not be linear. You would only have amplifiers being linear in an ideal case. So this means that the amplifier has a gain which depends on the signal amplitude or the frequency. Okay, all right. So basically, these are just the basic classifications of what? Amplifiers. So we would leave this here, and then we would look at it further in chapter 2, where we would look at large signal amplifiers, which in some literature they would call power amplifiers. So take your time and go through this over and over again, and then wherever you have doubts, just leave a comment with your doubt, and then we would together solve your doubt or clarify your doubt. Yeah.